All right, we're ready to start. Welcome, everyone. Thank you all for coming to support our seniors. We're excited to share all the work we've been doing for 9 months. Thanks, family, friends, faculty, sponsors, all of you for being here. We're starting off the day today with Team ME 23.2 Bolden's project. So feel free to come on up, team. Give us 1 second. All right. Okay. Welcome, everyone. We are Team 23.2 presenting the Vitruvitron 7000 workout machine. This is a collaboration between Bolden Product Development Services and Seattle University. So let's meet the team. All right. So to my right here, I have Dara and Brian. I myself and Madison. And then we have Emmanuel and Theo. Our sponsors are John and Allison up here in the front. And our faculty advisor is the lovely Kenya Mejia over here. All right.
Okay, so to start off, we're going to go over the table of content. We have 6 sections we're going to go over with you today. Number 1 is going to be the background. Number 2, motivation. Number 3 will be the problem statement. Number 4 is our solution. Number 5 is the future recommendations, and then we'll conclude. Go ahead. And to start off, for the background, we have a picture of John Bolden here. He used to be a former professional athlete. There you see him as a boxer. He suffered a career-ending injury, and after recovery, he became a personal trainer. And he also started the company Bolden Product Development Services, and his goal for that company is to help prevent injuries. And the way he intends to do that is providing exercise products that are fun and easy as possible to use. One of the products that's being developed at Bolden is the Vitruvitron 7000. A little information about that. The Vitruvitron 7000 is a concept at this point, and there's a sketch of one of the sketches that John provided to us, and it's an all-in-one exercise machine. Here's a preview of our CAD model and the physical prototype that we actually built. And before we actually go into more details about that, we're going to take a look at the motivation that started this project.
Thank you, Dara. All right, so as far as motivation goes, we've maybe all been to the gym and we're aware that there's traditional workout machines that focus on your major muscle groups. So this includes the upper body, the lower body, and your core. And this is great, you know, targeting those areas, but what about the areas like where the supporting muscles, tendons, and ligaments are? The neglect in these areas often leads to injuries. So a question that comes up is, how can we strengthen these areas? And a solution we have is full extension training. So what is full extension training? It is essentially performing exercises where your arms and legs are in a fully extended position in order to engage all muscles, tendons, and ligaments within that area, therefore strengthening all parts of that member. And this is awesome, but as you said, like back in the gym, you know, there's not necessarily a lot of machines that are actually targeting the full extension exercises. And there's a need for this because with the full extension exercise machine, we can then avoid injuries as well as activate the entire body. And this is awesome, and Bolden Product Development Services is working towards creating a machine that does this full extension exercise. And that is through the Vitruvitron 7000.
So next, we'll go into the problem statement, and we received a mock-up and some sketches from John, and from those ideas, we were able to decide what we wanted to do for our project. The first system we decided to focus on was the vertical gliding system. This system allows us to use vertical movements while we exercise in full extension, and we chose this system because we found that it's the most unique part of this product. Next, we focused on the gliding mechanism.
And we found that this mechanism is very critical in achieving the motion that we intend for. And lastly, we decided to omit any adjustability features. And these features allow users of different heights to be able to fit in this machine. But we decided to simplify the problem and design for specifically a 5'6" person, which is the average according to the CDC. And through this, we can create a proof of concept that shows the basic functionality of this product.
Okay, so as Brian mentioned, we're focused in on the vertical glider system, but what is the vertical glider system? You might be wondering, like, what is an exercise machine? Like, how does it start? We have to take a look at the intended range of motion, what you're trying to stimulate. So for our simplified version, the range of motion that we're looking at is the toe touch plus the leg lift. And here's a short animation that shows the intended range of motion for what we're doing. And from this intended range of motion, we created a proof of concept. This is only used for one side of the body because we can display functionality without needing to put in another one. Go ahead. So this is an overview of the system. You can see the frame and the housing that supports all the components. I'm going to go ahead and go over a little bit more details with you. The vertical gliders, there's an upper part that works the upper body, and there's a lower vertical glider that works your lower body. Go ahead. And we also have two different weight stacks, which is what makes the system really unique. There'll be two weight stacks working in parallel with each other. We also have the pulleys and cable that are routed to resistance and assistance training, and we'll go over that with you shortly. The next one is the cable carriage. This is where the user will make contact with the machine, where their hand will be placed and where their foot will be at. Go ahead. We'll go over more details about the pulley configuration.
Right. So right now we're looking at the upper vertical glider. So this is where your upper body is going to interface with the machine. And as you can see, the blue cables are used for resistance training. So this essentially means that the more weight you add, the more force that the user is going to have to generate in order to overcome that weight. So this will be for upper body, and then we have our lower vertical gliding system. So this is where the lower body will interact with the machine. And this is the more unique part of this machine because it's using assistance training. So assistance training essentially means that the more weight that you add will offset the user's weight and ultimately assist the user in performing that exercise, in this case being the leg lift motion. And if you have ever gone to the gym and used the pull-up machine, the pull-up assist machine, this is the same kind of mechanism.
So the cable carriage is the part of the machine that the user interacts with, following the glider path during exercises. It goes within the glider channels, rolling along the channels, and connects the weight stack to the exercise. It is shown here that it is in the vertical glider system, shown by 4A, which is the upper cable carriage, and 4B, which is the lower cable carriage. The upper cable carriage has a rounded handle for the user to hold during the exercises. The lower cable carriage is meant for the foot, where the left-hand side shows the mounting bar for the foot panel, and the foot panel is shown on the right. Since the upper cable carriage and the lower cable carriage use the same function, I will be continuing with just explaining the upper cable carriage. During the design decisions, which we have over here, we had to focus heavily on the space within the glider channel. As you can see, it's pretty small. It's 1.25 inches, and within that space, we had to fit the rolling mechanism and the connection point between the weight stack and the exercise. Shown here, the cable was routed throughout the glider channels to the handles, which were mounted by cable eyelets and a bolt. We did this on both sides to create an equally distributed load during the exercise for smooth rolling. We also decided to use 4 bearings on each side of the cable cart. This is because, or 2 on the upper side rolling along the inner channel, top side, and 2 rolling along the bottom side of the channel. This was so that it can have a smooth glide and distribute the weight of the user upon the glider.
Yes, thank you, Theo. And the next thing we did was to analyze all the parts of the machine. We used the ANSYS finite element analysis tool to look at the total deformation as well as the equivalent stress of each critical part in the machine. As you can see in the diagram here, I have the upper vertical glider, which is mounted by 2 bolts on both lower and upper parts of the glider. And the force is applied, about 250 pounds, or 250 pounds was applied along the inside of the rail, the glider. This is when the user would be fully extended all the way down, and the cable would be resting on the inner part of the glider. As you can see, there's different colors there. You have blue to red, blue meaning the least amount of deformation, red meaning most amount of deformation. The amount of deformation we saw was about 0.014 inches, where that's very little amount of deformation and it's not very major in our case. And keep in mind the video is showing an exaggeration of what is actually happening. It's probably moving even less. So. And the other thing to look at is the equivalent stress. The equivalent stress is kind of the total stress of in all directions, kind of pointing in one direction. In this case, we have the lower vertical glider, which is very light speed, and we also have the 2 bolts on both top and bottom of the glider holding in place, where the cable would be routed on the outside as well as on the inside. So you have the 2 arrows on both inside and out. And you have the same 250 pounds with the weights and the person using it, where blue is the least amount of stress, red is most. In this case, we had around 400 PSI of equivalent stress.
So now that we've gone over our solution, we can go into future recommendations, and considering how far we were able to come with this product and how much we were able to learn. The first thing we suggest is starting initial designs with the adjustability, and more specifically, this is for users of 5 to 7 feet tall. These features are located on the handles, the foot panels, as well as adjustments in the glider position itself. We also suggest improving the physical testing. Currently, our prototype holds around 60 pounds per weight stack, but we think that a more ideal load of the 250 pounds, which is the max weight of the Vitruvitron 7000, would be ideal for informing us on the structural stability of the machine. Next, we also have improving design details, and overall, this is just a process where we can streamline the assembly process, as well as help the next iterations create a more simple version of the machine. And in conclusion, we were able to achieve many things with this project. The first thing we achieved was the resistance and assistance training, which you can see in the pulley systems that we've created. We also developed a gliding mechanism, which can be seen through the cable carriage. And through all of this, we created a viable proof of concept. And in conclusion, we established a foundation for full extension exercises that can help John move forward with this project, as well as the next iterations to come.
All right, and with that being said, we'd like to take some time for some acknowledgements. And we really just want to extend our thanks to Bolden Product Development Services for all of your just constant support with us in this project. Yeah, I mean, obviously you are awesome. And same with the Project Center, because we obviously want to have this project with Bolden. And then as well as all the faculty here, y'all have supported us in many ways, especially with our random questions, you know, anyways. And we also really want to give a huge shout out to Mal, the lab manager, because Mal is awesome. He put in a lot of time with us and just let us use everything in the machine shop, especially the CNC for those cable carriages, which was really cool. And then just all of y'all for being here. Thank you so much. And with that being said, thank you. Any questions? Great question. I think just, especially this year, this is like the first year for us seniors to actually really be together because of COVID. So this was our first like real team experience, within the department. And for me, I think it was just awesome to be given this opportunity because we didn't have a say in who was gonna be on our team, it was picked for us. So with that, like, you're gonna have to learn how to work as a team and be a teammate. And we definitely had to do that and just be there for each other, support each other, and listen to new ideas and just be open with each other in order to be successful. Which I think we really got to get to know each other, put a lot of time in. Yeah, I think I'm definitely gonna miss this team. I think I can speak for everyone, I hope. Yes.
Is there any user safety issues that you had to consider?
Yes, absolutely. So, for making an exercise machine, there is the ASTM standards for a fitness machine that have to be considered. And one of the main, components within those standards is meeting a safety factor of 4. So that basically means that the strength of your machine needs to be 4 times the intended load that it's gonna endure. So we definitely had to take that into consideration when picking out what materials are gonna be made, as well as like the different bolts and, yeah, all those sort of things. Yes.
How did you guys figure out the shape of the curved rails? It didn't look like they were perfectly circular. Is there a method that you used?
I can go back. Here, Brandon.
Sorry, could you explain the question again?
Yeah. How did you determine what shape the curved rails needed to be? Is it perfect? Is it perfectly circular? Is it an oval?
Yeah, so the shape of the machine ideally would be based off of, I guess, the biomechanics of a human. Considering our intended range of motion, the exercises will be performed like both the top and the bottom at the same time. So you'd be hinging on your hips. So that means that the radius of the upper half would be your hips to wherever your arms go, and the lower half would be your hips to your feet. That's how we decide the shape, but for our physical prototype, we were restricted by the parts that we could find off the shelf, I mean. So this one is designed pretty closely to our average that we calculated, which is, I think the bottom is supposed to be around 35 inches and the top around 43. But these are both 3 feet inner radius, so it's pretty close to what we wanted from our calculations.
Come check us out at our poster if you want to see our physical prototype. It's awesome.
All right, next up is team 23.3, Kenworth.
Hello, we are team ME 23.3 with the Kenworth point-to-point package delivery system. Our sponsor advisor is Jeffrey Spalding. Our academic advisor is Sam Holm.
I'm Ethan.
I'm Peter.
David. And I know.
little sneak preview. So let's talk a little bit about the Kenworth Truck Company. So Kenworth is a industry-leading commercial vehicle manufacturer based in the greater Seattle area. They are currently developing a wide range of commercial vehicles and are pivoting to develop new battery electric vehicles to meet the demands of zero emissions regulations and environmental concerns. So let's take a look at a daily application of a Kenworth truck. On the left, you can see Kenworth's flagship battery electric vehicle located outside Project Falcon. And on the right, you can see a typical route the Project Falcon may take. This may be from Seattle to Portland. Now, most routes are going to take the I-5 from Seattle to Portland. This results in approximately 3 hours of driving, 170 miles. Now, this is given that there's no traffic and that it's pretty decent conditions. But what happens if I-5 is closed? Maybe there's a landslide, maybe there's a lot of traffic, we need to go take a different route. We have to take a detour. Now, commercial, traditional vehicles don't have any problems with detours. Detours may add a lot of extra time, they may mean you miss certain deadlines, but the car should be able to get from point A to point B. This is because traditional combustion vehicles already have a lot of infrastructure built. Project Falcon and other commercial battery electric vehicles lack a lot of this infrastructure. And so for us, the question becomes, can we take this detour? You can see on the right, this detour results in approximately 5 hours of drive time and 202 miles of driving. So this is an additional 30 miles of driving and 2 hours of drive time. Now this may be totally fine, and this may be totally doable, but how can we characterize this? This is the problem that we're trying to solve. Kenworth tasked us with building a battery electric vehicle with a corresponding energy modeling system. So, or energy monitoring system, so that we can integrate it with a energy modeling system and predict the behavior of battery electric vehicles along different paths and different speeds.
So in order to solve this problem of building a reliable energy model, first we had to build a battery electric vehicle prototype that was able to measure the energy consumption of the main components of our device. We also need to determine important factors for our energy modeling system that we took into consideration that we'll be talking about later. Then we went on to test and measure the energy usage of our battery electric vehicle and input this data into our predictive model to tune and validate our process.
So let's get into our project. We're going to talk about our project in two sections. The first section is the battery electric prototype, and the second section is our predictive model. So let's get into our prototype. When building our prototype, we wanted it to satisfy 3 requirements. The first requirement is that it has independent driving and steering systems. This means that the system that drives the cart forward is completely separate than the system that drives the cart, or not drives, that turns the cart left and right. The second requirement is that it follows an autonomously chosen path. This means that when we set a path onto our prototype to run, it will run that path without any human intervention until it reaches its final destination. And the third requirement is that it can monitor its energy usage when it goes through that path. Now you know what our prototype should and can do. Let's see how it all works. So this is our basic version of our steering mechanism. It shows that the wheels will turn simultaneously and that when going through a turn, the inner wheel will rotate a little bit more than the outer wheel. This is important because when a car or a vehicle is going through a turn, the inner wheel will have a shorter turning radius, meaning a greater turning angle. And when I play this video, it will show that the wheels will turn to the right and the right wheel is turning slightly more. Now you know how it works. This is our final designed steering mechanism. It is powered by a servo motor, you can see right here, and then linkage arms on each side. And to connect the servo motor motion to the front wheels, which are located here, we designed a wheel interface that can sit in between that square extrusion that allows it to rotate easily and support the weight of the cart. Now, how do we drive it? We designed a drivetrain, which consists of a motor here, coupled to a gearbox, dual output gearbox that has axles on each side. These axles will have wheels fixed onto them. And to add more support, we added bearing housings on the outside of our drivetrain. After we designed our steering mechanism and our drivetrain, we manufactured and assembled our battery electric vehicle. As you can see, here's our servo and the steering mechanism and the motor and the drivetrain. You might be wondering, where are we going to put our package onto this cart? There's not enough room on that. That is why we designed a package platform that goes over the top of our cart, which has enough room and support to hold our package, or in this case, our 10-kilogram load.
Now to go into a little bit about how we control our battery electric vehicle. We use the Arduino Uno microcontroller in order to control our cart. And it is coded to have two different paths, or a straight path, a circular path, where the user can decide what the speed is, what the turning angle, or for the radius of the circle is. And then with that code, it executes and communicates to the motor, which drives the cart, and also communicates to the servo, which turns the wheels. As far as collecting the data, we use the M4 Airlift Lite microcontroller, which is used coupled with three Hall effect sensors. Each one of those is using the current, or is measuring the current from each of the components. Our components are both the microcontrollers paired together, the motor and the servo, and when multiplied by the nominal voltage for the cart, we're able to determine the power for each of the components in the overall system. Moving into our testing, our methodology, we conducted 5 different trials at 4 different speeds, which this was vital in order to help build our energy model system. And so those speeds were at 0.5, 1, 1.5, and 2 meters per second. And then we continued further iterations of 2 meters per second and calculated out the power consumed for each of the components in the overall system.
The second part of our requirements was to build that predictive model that we've been talking about. It must calculate the expected energy across our paths given the chosen path and the chosen speed. We also need this data so that we can tune and validate our battery electric vehicle. So the way that the power model works is we have our initial driving conditions inputted into both our battery electric vehicle and our cell model. What the battery electric vehicle does is it runs through the specified path and the speed, and then the electric current sensor sense the current, and then using the nominal voltage, we can calculate the actual power consumed. What the cell model does is it takes those same input driving conditions, and then it automatically calculates the power consumption, and then from there we can compare the actual versus the predicted power.
So let's take a little closer look at how the model actually works. So on our experimental cart, our model works by monitoring the electrical current usage of each of the key components, this being the servo, the motors, and the microcontrollers, and multiplying that current by a nominal voltage to get the power consumption. In our mathematical model, instead, we're using the physical position of the cart in space and time to develop how much power and energy is being used. So let's get a simple case of forward motion. Here you can see a cart moving forward. As the cart moves forward, each of the wheels rotates, and there's reaction force on each of those wheels. This rolling resistance means that if we know that the vehicle is moving forward, it must consume at least as much energy as this rolling friction consumes. And so knowing this, we can take the friction force and multiply it by either length or speed to get work, which is the energy used by the actual vehicle, or power, which is the energy used over time. And so if you notice both of these terms, if we're assuming that we're not changing the path length or the speed, we can assume that at steady state conditions, we'll see perfectly flat lines.
So going through our energy model, we had 2 criteria that we wanted to focus on. The first one was while our battery electric vehicle was going straight, and then also while it was turning. When it was going straight, all of the wheels were turning at approximately the same velocity, and they were going the same direction. However, when the vehicle is turning, the turning angle for the front wheels versus the aft wheels are at different angles. And this causes scrubbing or added friction between the wheels and the ground surface. This increased friction causes more power consumption by our overall system. So here's some data that we go, and on the left here, we have all for our whole system, all three components where most of our power is being consumed by the motor. Very little was actually consumed from the microcontrollers and from the servo itself. So over here on the right, we have our the data that's up top is through the curve, and the data that's on the bottom is for while it's going straight, and we have the raw data compared with our predictive data, and it is very similar to each other. And so we're able to prove and to tune our systems.
So why should you care? As we talked about previously, battery electric vehicles are the future. It's estimated by 2050, all vehicles on the road in the United States will be electric. And this is great. And we can already see consumer vehicles taking the plunge. And this is good for both consumers and the environment, as they're cheaper to operate in the long run, and they're also more environmentally friendly. We can see pioneers like Kenworth spending a lot of time and money developing new battery electric vehicles to meet government regulations and environmental concerns. Likewise, as we move forward, energy modeling is going to be bolstered by predictive energy. But energy monitoring is going to be bolstered by predictive energy modeling. This is important because as we increase the number of vehicles on the road, it becomes incredibly important to be able to characterize and predict their energy usage. And so one of the key concerns with both battery electric vehicles and traditional vehicles is their weight. On battery electric vehicles, this means that the more batteries we add to an electric vehicle, the less cargo we can carry. By using predictive energy modeling, we hope to be able to optimize the number of batteries on these vehicles and minimize those batteries so that we can carry more cargo. Likewise, energy usage is an incredibly important part of battery electric vehicles. Not only energy used by the vehicle itself, which is incredibly important, but also the strain that the vehicle puts on the energy grid. By characterizing and predicting the energy use of the actual vehicle itself, we can use that to actually build our energy grid to match. And then lastly, energy storage is another incredibly important part of battery electric vehicles. Moving forward, battery electric vehicles need to build a lot of infrastructure. Current battery electric infrastructure is in its infancy. And by using predictive energy modeling, we hope to be able to take and place new charging stations in places where we can optimize the efficiency of battery electric vehicles to carry more cargo and have less batteries. In short, predictive energy modeling is a tool for allowing us to build more efficient battery electric vehicles to carry more cargo. Thank you.
I have severe anxiety and procrastinating, and I'd rather be up here with my team and the questions in the Q&A. Where's the answer?
Battery technology is constantly changing. Did you take that into account?
I think in this project, one of the things that Kenworth is dealing with is their large Project Falcon battery, and they're feeling the same effect that you're talking about. As the batteries are changing, and there's a lot of movement in the industry, and I think moving forward, it's incredibly important for us to look at that. One of the ways that we were addressing this problem is by optimizing the energy usage, because as batteries are being developed, they're getting smaller and lighter. And that's a key, an important part of battery electric vehicles. But currently, we don't have adequate ways to measure that energy usage. If we talk about Kenworth's traditional combustion engine vehicles, they pioneered new ways to measure the fuel efficiency of those vehicles so that they could create more aerodynamic vehicles. And likewise, our scope is to try and help Kenworth develop new strategies for developing battery electric vehicles and monitoring of that, so we can address the new changing requirements.
I noticed that on your cart, the wheels in the front, and if they were further apart than the wheels in the back. If I'm looking at that right, I was just wondering why you guys did that.
Yes, so the reason why the back wheels are closer together, it's because our gearbox is not a differential. So what a differential is, it's basically a gearbox that can allow each axle or wheel to turn at a different rate. So like when going through a curve, that one wheel will have to rotate more than the other wheel. So since we didn't have a differential, we decided to put the wheels closer together since they have to act like one single wheel. So the distance they travel is more the same than if they're further out. It's in the back.
How do you know that the data you are collecting is credible? Like, is it just compared to your mathematical model, or is there other validation process?
Yeah, so one of the ways that we validated this data is that we took, we used a couple different Hall effect sensors and a data processing algorithm. So if you don't know anything about Hall effect sensors, they're notorious for being noisy. And so one of the ways that we were able to validate that is by taking a bunch of data on the Hall effect sensors and comparing it to a benchtop power supply and using a reference voltage and reference current, and then comparing and tuning our data collection algorithm that suit.
I suppose it's fair, not my bad, no.
Come on, you got it.
Oh,
No, I haven't checked this.
Yeah.
Okay, so we are team 2310. We worked with Kenworth and we were working with predicting sales code driven REIs. So the team, this is Titus, Greta, Twan, Jordan, and Cameron. Our advisor was Professor Susan Reeder, and then our sponsors were there, were Nick Grant and Jerry Bishop. So you heard a bit about Kenworth from the last team. but they're a Kirkland-based truck manufacturer specializing in medium and heavy-duty trucks. They've been manufacturing trucks for 100 years, and specific to Kenworth is each truck order can be specially customized to the individual customer's request. So the problem is for each truck, because it can be specially customized, different sales codes and option approval requests will not always match up, and there'll be part conflicts. These part conflicts are going to be generating a request for engineering or an REI, where an engineer will need to fix the part conflict in the bill of materials. So we'll have to go through, let's say a wheel doesn't work with this tire rim, it's going to generate an REI, and then a engineer is going to have to go through that and fix the bill of materials. And these REIs can take up to 45 minutes, and each truck order is going to have many of them. So our vision was to create something that would allow Kenworth to predict how many REIs per truck order, so that engineers can have a better workload estimate. With that, our mission was to work together as individuals and as a team to utilize our collective individual knowledge to make a model, and then also produce a quality product for Kenworth. So again, our goal was to create an effective machine learning model to assist in predicting part conflicts due to client customizations on trucks.
All right, so next I'll be going over the data pipeline, which basically provides a high-level overview of how data is processed. So this starts at the customer-facing side of the sales tool, where customers are allowed to put in custom orders to their desire. From there, that order is passed through the mainframe to process and put it into their respective place at the data sources. At that point, the sales order is converted into a bill of materials to be used for production and then stored in the Snowflake data warehouse for ease of use. Then next, I'll go over the project design overview, which basically showcases what we have done over the last year. So starting in the winter quarter was a heavy data exploration phase, which consisted of adding truck chassis attributes, additional sales code categories, and implementing a metric known as a TRA statement, which refers to the first layer of logic when a sales order is turned into a bill of materials. This metric would be a complexity metric. From there, we cleaned and filtered the data so that we could use it in the model, and finished off that quarter by refactoring last year's ML model so it'd be ready for our updated data set. And then kicking off spring quarter, we started testing the data with the ML models and implemented other models that might fit our updated data set even better. We compared results, created documentation so that we could pass it off to future teams, and created visualizations to support our findings. And then we selected the most accurate model, which we'll expand on shortly.
So I'll talk a little bit about the technology that we use throughout the project. So we use Python as our coding language because it has a lot of machine learning libraries that we can use, and we also use Visual Studio Code as our development environment. We also use Amazon Workspaces, as that was the virtual environment that Kenworth gave us, and GitHub to share the code among our team. We also use Snowflake to pull in the data from Kenworth and Tableau to visualize all the results. And we also use Lucidchart to create data diagrams to understand the flow, and Azure DevOps to keep track of our past incidents. So throughout this project, we did a combination of both Agile and Waterfall. So we used 2-week sprints, and we had a total of 12 total sprints, but we still adjusted to our sponsors' feedback. So here are the 2 major milestones that we completed throughout the project. I'd say for the end of winter quarter, it was completing a data set. So that would include pulling in a lot of data from separate databases and putting them all together so we could put it through the machine learning model. And then for the end of this quarter, we refactored the random forest model that was created from last year and created 2 other models, ridge regression and XGBoost. So here are 2 of the major blockers that we faced throughout the project. I'd say the first thing was the workspace permissions. So that would include the firewall that was blocking us from downloading certain extensions that we needed for our project. And also GitHub was another blocker, as we couldn't, it was hard for us to have good version control. Another thing was the shift in relevant data. So we realized that we had to change the project, the scope of our project, and we also had to figure out that some of the data was getting put in another database that we had to pull in, and then some of the data was also getting canceled that we were still registering.
All right, so as you can see on the screen right now, we are having 4 images of the 4 root of the input feature that we have in our data set. And for the first one, in the upper table, we have the general information about the shop and the order. And in that table, we have order number and chassis number, which is the MF-ORD-NO. And then we have shop model. Then we have tentative schedule date, which is used to differentiate shop for different years, because there is a small possibility that a shop from different years will have same chassis number. Then we have ORAs, which stand for optional approval request. And last one is RAIs, which is the one that we want our model to detect. And for my right hand side, the first table will show some of the chassis attributes that we find during this project. And chassis attributes is the characteristic on the feature of the shop chassis. And the reason why we decide to bring in chassis attribute is because that when the customer wants to customize and configure a shop, there's some certain part on some certain configuration will require changes or addition to the shop design, and this will lead to more number of RAIs. And then in the middle, we have a table of cell code. We see the code to use to identify the configuration option or feature that are available for a certain shop. And we bring in this data from the last year work. And last one is the TLA count, which is referred to the first layer of logic when the order created in the cell tool and go through the mainframe, as we mentioned before. And we have a theory that if the shop with a higher TLA count, it will have a higher complexity when it translates to the bill material. And this also may cause a higher number of RAIs.
All right, so next we dive into the models themselves. So the first thing we looked at in each of these models was the feature importance, which is basically which pieces of our data are most important for determining how many RAIs an order is going to generate. So as you see up here, here's one of the example charts for feature importance of our models. Each model generated a different chart depending how it's training, how it's testing, and so there's several different iterations where some features are more important than others, depending on the model, depending on the data we used at that time. So once all that's gone through and set up, we are able to test and train the model and get some results back for that. And so we use 2 metrics here. We use a symmetric mean absolute percent error, which basically measures the error rate of the entire model, the percentage it's off by. And then we use the mean absolute error over here, which is a distance between the actual versus the predicted values. And so we'll start with the simplest model we use, which was ridge regression. It had around a 44% error rate. That's just because of how simple it is. It doesn't mesh well with the data we use and the complexity of it. And so then we tried out last year's chosen model, random forest, with our new data set. Performed well at around 32%, but we could still do better, and that's where XGBoost came in. It's a bit more recent of a model, and overall it gave us around that 30% error rate, which is what we were looking for. Then you see that decreasing trend in these models displayed in the mean absolute error, where ridge regression has about a 2.4 mean absolute error.
And that decreases to 1.8 in random forest and down to 1.7 in XGBoost. So here's a couple plots for each of the predicted versus actuals for our models. You'll see that black line on each of these graphs is where the predicted is equal to the actual. And so that's what we're looking for when we plot these data points. So you'll see the accuracy reflected in XGBoost as the clustering of these data points is towards that black line. There's very low spread apart from some outliers here and there. This is not as reflected in the ridge regression graph, which is down in your bottom right. And so there you see the spreading, it's all over the place, and that's accounts for that decreased accuracy. And then finally, you look at the random forest plot, and you'll see there's a lot of clustering similar to how XGBoost was. But as the REIs, or the actual REIs grow larger, you'll see a large overprediction of the predicted REIs. And so that's where some of that inaccuracy comes into play. And so Tuan's going to talk about what's going on with this model moving forward and what these results could mean.
All right, so during working together, we have learned some valuable lessons that we want to share with our team. The first one is to ask questions and approach blocker early, because we realize that many of the problems that we encounter so far that will be this can be so much faster if we approach it early, or we ask our sponsor earlier. Secondly, to communicate with sponsor. We agree that with the experience and advice from our sponsor, it's helped us to get a better idea inside the project, so we can figure out what is the next step toward our final goal. And next is to communicate with our team. So this will allow us to say our idea and understand what other team member is doing, so we can increase the completeness of our deliverable that we hand to our sponsor. And last one is to start more and build up. So over the course of this project, we have been more focused on the big picture, and this prevents us from working effectively and figuring out what is the next step toward our final goal. So we shift our focus from big picture to starting more and build up to our final goal. And what's next? So as the projection assistant, we have some future recommendations for the next team to consider. The first one is to tuning the model hyperparameter to find the optimal combination of value that can increase the accuracy of the model. Next one is to test out a model to see if there are any different machine learning model or classification algorithm that fit more to our data set and have a better accuracy than the model we are having right now. And the last one is to find another reason for the REIs, because one of the goals that for our project is to find the reason that's triggering REIs. So that's why I believe the last task right here is an important task that the next year should consider. And that's bring us to the end. Thank you for your listening and attention today. So Telescope can drive like the whole part of the drug that you get power fire off even your clustering model predict that correctly, where you like really take the search fire off
So the models, as Jordan said, there's feature importance. So certain features will have a higher importance in the model. And that importance will drive like the accuracy. So different parts there. That answer your question? Or?
Start the presentation. Personally, I have no idea what that means. What is REI?
Yeah, so an REI is a request for engineering information, and it occurs when there is a part conflict or a complication in the bill of materials. So if a certain wheel doesn't match with a tire rim and it's on the bill of materials, that's going to fire off a REI, and then an engineer is going to have to go and manually fix the bill of materials. Any other questions?
So you talk about how you had to rank the importance of different components. Why is that a necessary step? I don't think that much here. Why is that a necessary step for making the model run effectively? Can you talk a little more about that?
Sure, that's not to make the model run effectively, it's more of an analysis of the model itself. So that's determining what part or what features, in this case, it's specific sales codes, are most important to the model itself. So to make the model run, we're putting in a bunch of data, so several thousands of rows are getting put into the model, and that's going to, that's where the training stuff comes in, where you train the model, and this is an analysis part.
I'd also like to say there are instances where these features actually have a negative effect on the machine learning models. So they will hamper the results and kind of clutter it, and overall it just makes it harder for the machine learning model to function.
Okay, thanks.
We now have a 10-minute break, so we can meet back in this room or any other room you'd like to go visit. See you all soon. All right, welcome back, everyone. We have two teams presenting in this session. And we're gonna start off with ME 23.5 OCR. Thank you.
All right, cool. Thank you all for being here today. It's an honor for us to be here. We are team ME 23.5, and we've built the proof of concept prototype for the laparoscopic surgical zip tie applier. Our sponsor is OCR Consulting, and our team is made up of Madeline, Kai, Sophia, Sam, Migio, and our faculty advisor, Dr. Ren. So before we get started, we'd just like to make a quick overview of what we'll be presenting. So we'll give a brief introduction about our project and our sponsor, and then we'll talk about what laparoscopic surgery is and the reasons for we are developing this project. And then we'll go over how our prototype works, its key components, and the outcome from this project. So our team's mission is to build a device to make laparoscopic surgery safer for patients. And the goal of our project is to create a prototype for a surgical instrument that will be inserted inside the body to seal any ducts or blood vessels using zip ties. And our job is to prove that such a device is possible and to prove that all its functions and mechanisms work correctly. So our sponsor is OCR Consulting, which is a medical device development consulting company. And the device development consultant of OCR is Dr. Stephen Kerr. And we worked with him in developing the idea and concept of the surgical zip tie applier. And together with him, we created the device prototype with the help of his extensive knowledge and experience in laparoscopic surgery.
So at this point, you've heard laparoscopic thrown around a lot, and you might be wondering what that actually means. Laparoscopic surgery is also known as minimally invasive surgery, and this surgery is typically performed during organ removals, such as a gallbladder removal or a hysterectomy. To perform this procedure, small incisions are made to the abdomen of the patient's body. Through one of these incisions, a laparoscope is inserted. A laparoscope is a very long and thin medical device that has a camera and a light attached to the end of it, which provides visual feedback to the surgeon while performing this procedure. Afterwards, another device is inserted through another incision, and that device is used to specifically seal off any ducts or blood vessels that are going to be cut during this procedure. This is an image of a gallbladder, and gallbladders paint a really great picture of why you might need a seal to perform this type of procedure. As you can see, connected to the gallbladder is a cystic duct that connects to the common bile duct. If the seal is not applied perfectly, then the bile duct will leak into the patient's body and cause severe complications. And this goes for many other types of procedures. With any bodily fluids leaking into the body, the patient will be severely sick. So currently, there are two products used to apply these seals. There's a surgical clip and a Humalog clip. The surgical clip tends to fall off the duct of the patient, especially when the duct is severely inflamed and then that clip is applied. The Humalog clips have teeth on the ends of them, and those teeth might cause punctures to the duct, leaking regardless if the seal was a perfect seal or not. Both of these products also are inflexible, so they might not get the perfect seal that the ducts may need. So the purpose of our project is to reduce the complications associated with these two products.
So our product is going to use a zip tie to hopefully eliminate some of the issues that Sophia was talking about. So we're using what we're calling a surgical zip tie, as pointed here on the image. This is just a CAD model of our final design. And so basically we're taking pre-existing zip ties that you're commonly familiar with, and we modified them. For our prototyping, we actually developed our own and 3D printed them, which is super cool. And so what happens is this is where the duct would go into our prototype and then the zip tie would tighten around it. If you go to the next slide here, so on the left, this is just a picture of one of our 3D printed prototypes, and then on the right, this is just a CAD model of the standalone zip tie. And so how it's tightened is we insert a hook through the head of the zip tie. We make a little T section there, and the hook goes through the head of the zip tie and then engages with the tail of the zip tie. And when it's engaged with the tail of the zip tie, then the hook goes back through and drags the tail with it, which is what creates the tightening force.
So here you see it's like prototype of our, it's an overview of our prototype. As you can see from the picture, we have our key components labeled. Starting from the left, we have the plunger, spring, pin system, internal supports, which there are 3 of, the hook, and then our most critical component, the cartridge and the surgical zip tie. So first, the plunger will be pushed down. The hook will go through the cartridge and the surgical zip tie. The hook is engaged with the surgical zip tie through the use of springs. And lastly, it's ready to be pulled through the cartridge using the handle. So again, here's just an overview of the animation. So here's a close-up of the interactions between the hook, the cartridge, and the surgical zip tie. First, it will be at resting position. Next, the plunger pushes the hook through the cartridge and the surgical zip tie. The hook stays engaged with the surgical zip tie. And lastly, it's ready to be pulled through the cartridge using the hook. So here's the animation. The hook goes in, engages with the zip tie, pulled through the head of the zip tie and the cartridge to desired size.
So now I'm going to talk about some of the detailed design choices that we made in our device. I'm going to start with the cartridge. Shown on this image, this is the red part of this as labeled. And so the purpose of the cartridge is really important. It's what houses the surgical zip tie itself in our device, but it also provides the interaction point for the hook and the pin system so they can interact with the surgical zip tie. Go back quick, sorry. It's also on the end of our device, so it's the part that interacts directly with the organs in the patient. So its design is not only critical for the function of the device, but the safety of our patients. So when talking about the design, I'm going to bring about one of the issues that we had with one of our initial prototypes, which is shown on the left here. So this tubing is mimicking a duct inside a body. And so when we tighten the zip tie around the duct, as you can see, it's tightening against the cartridge itself instead of just the head of the zip tie. And so when we tried to release the zip tie after tightening it, it was stuck to the cartridge and we couldn't get it out. Or if it did release, since the cartridge is no longer there, it would not create a perfect seal because there's added space. So what we did is we basically moved the zip tie down in the cartridge a little bit, which is shown on the right here. So as you can see, when the zip tie is tightening around the duct, it's no longer touching the cartridge and that issue is no longer there. So to make this possible, we had to do a few things. One of those was the addition of tapered grooves. And so these tapered grooves basically just hold the zip tie in place in the cartridge and prevent like vertical movement so the zip tie can't move up and down. And then we made them tapered, so when it's time to release the zip tie after tightening, as soon as the zip tie moves a little bit, there's no longer that pressure between the grooves, which severely reduces the friction, and the zip tie just falls right out, which is perfect. Next, I'm going to talk about some of the features of the surgical zip tie itself. The first of which is just going to be the inverse of the cartridge groove, so it fits within the cartridge well. And then the second of which is a bump on the tail. And so we added this bump on the tail. Again, I'm going to reference one of our previous designs. So on the left here, this is one of our initial designs. As you can see, in between the tail and the head of the zip tie, there's that gap there. And so that's not creating a very tight seal. So we added that extra material, and shown on the right, that gap is severely, it's much smaller, which is great. I'm stronger signal.
So the last detailed design that we're going to talk about is the pin. So as you can see, there's two parts that made up the pin. So the first one is the internal supports, which consists of like 3 identical pieces along the tube, and the pin system, which consists of a lever and 2 pins. So the main purpose of the pin system is to maintain the alignment of the surgical zip tie as well as securing its position. The reason behind that is we don't want the surgical zip tie to accidentally come loose or dislodge the cartridge during the operation when it isn't supposed to, because it will raise the risk or hazard to the safety of the patient as well as delay to the operation. So this is just a top-down view of what it looks like for the cartridge in the loaded zip tie. To if it's like aligned versus misaligned, we want to prevent that misalignment to happen. It's not just that the surgical zip tie will fall off, but as well when we flange the hook down, it might caught up somewhere and will cause jam that will add another delay to the operation. So this is just an animation of how the pin system works. So first, the surgical zip tie will be loaded to the cartridge, and then the lever of the pin system will be pushed forward to secure it. And then once the surgical zip tie will ready to be released, then the lever will be retracted back to its original position. And now the zip tie is unsecured and it's ready to be dislodged, as you can see in this animation. So lastly is the internal supports. As mentioned earlier, there will be 3 identical pieces along the tube. Each pieces will have a cross-cut holes where the hook and the tail of the zip tie will go through, and also 2 circular holes for the pins to go through. The main purpose of this internal supports is just to prevent deflection for the hook and the pins. So this is just a quick animation to show where those internal supports will be located throughout the tube, and also how it supports and guide our hook when it's plunged down and also retracted back.
Right, so this is our final prototype. To quickly summarize what we talked about, we have the plunger and handle that moves the hook forward and back to tighten the zip tie. We have the pin system, which engages and disengages the zip tie. Then we have our internal supports, which prevent deflection in the pins and the hook. And then we have our cartridge, which secures the zip tie in place. And lastly, we have the surgical zip tie, which is used to seal the ducts. Put everything together and you'll have the laparoscopic surgical zip tie applier, a surgical instrument that can seal any ducts or blood vessels and without the risk of puncture or slipping off, making it safer for the patients. So before we end our presentation, we'd just like to thank our team members and our faculty advisor for bringing this project to a success. And we'd also like to thank our sponsor, OCR Consulting, Dr. Kerr, the Project Center, and the Mechanical Engineering Department for giving us this amazing opportunity to practice and develop our skills in engineering. And last but not least, we'd like to thank our friends and families in the audience for supporting us. This is your success as much as ours, and we really couldn't have made it this far without your support. So thank you. All right, we'll now be taking questions.
You didn't do any animal testing or any?
No, we did not.
How does the zip tie in size compare to like the things that you're competing in the market? I don't know that.
Yeah, definitely. So this prototype was, in case I don't know if we mentioned it, but it's twice the size of our final product. Our main goal here was just to prove the functionality of the design. So there's a lot of those details when we look at like what the actual final products look like that we haven't figured out yet, and that wasn't really part of our project. In general, the surgical clips and the hemolocks are pretty small, so the zip tie would probably be bigger than those. But compared to the zip ties we were using, it's going to be much, much smaller. That's a really good question.
Did you do any research or investigation into what type of material you would make this out of in a more final product? You said, I think you said 3D printed this prototype, right?
Yeah, that's a great question. So Finding like biocompatible materials, again, wasn't really part of our project, but definitely something we thought about. So Hemalock clips, which is one of those competitors that we were talking about, I believe are made out of nylon. And so that's something that's biocompatible and works when it's like living in the body permanently, which is what the zip tie will be doing. So that's an option, and it's like works well with zip ties. It has the right elasticity, and that sort of thing.
Awesome, cool, thanks.
Yes.
How do you know what kind of a maximum force or minimum, so that it will not leak, but it will not be so tight that it will fall off or do other damages?
Yeah, that's a very good question. So in laparoscopic surgery, they use the laparoscope has a camera at the end, and the surgeon can tell will be able to tell how much just by feeling they can sorry so there's a tactile feedback in the device, and yeah, they'd be able to tell how tight they need to tie the zip tie to make sure it's not too tight.
I'm gonna jump in on that question too. There's also, so with the laparoscope, there will be visual feedback for the surgeon as well. So they'll be able to be in the body of the patient while they're tightening the zip tie. So they'll be able to see just how tight. We don't have the numbers of like how much force is required. But with those two methods, we can provide a secure enough seal for the patient.
So I don't know if I missed it, but is there like a way for you to cut the piece off after you hold zip tie or?
Yeah, so right now, implementing a cutting mechanism in the zip tie applicator is currently outside the scope of our project. But we did do some conceptual work and drawings when we first started the project about how that might look like. And I guess the biggest challenge we foresee from that is the implementing the cutting mechanism will more than likely interfere, at least currently, with the other mechanisms, because the hook and the pins are already taking up most of the room inside the small tube. And another problem with that is the effect of scaling down the prototype. So right now our prototype is double the size. And when you scale it down to the size of the intended final product, you'll need a much smaller blade to cut the zip tie, and it'll make it very hard to cut the zip tie. Also, another challenge from that is just we don't have enough fingers that would be free to move to like activate those mechanisms. So you have, so we already have the thumb, which pushes the plunger down, and yeah, pushes the plunger down to tighten to engage the zip tie and provide counter pressure so that when you squeeze the handle, so that you don't just take the device off. And yeah, and you have the index finger, which stabilizes the handle, and then the 3 other fingers, which actually squeezes the zip tie. So yeah, it'll be hard to to put it together at this moment, but I guess those are some things to be mindful of for engineers who decide to continue our project.
Yeah, I think like we all know that like zip ties, when we tie them, it's kind of hard to like loosen them. And I feel like in this case, there may be potential for to like tightening it too much. Is there any function on this that loosen zip ties?
Yeah, that's a super good question, and one that we haven't gotten all year. So congratulations to you. Yeah, so like zip ties don't release, that's kind of the point of them, and so that's not something that we have really considered, during a surgery, there's lots of other options to like. I mean, when you have a tight zip tie, you basically just have to cut it off, I don't know if there's another way to easily do it. So during surgery, there's a lot of other options, you can create a seal on the other side and then just cut the zip tie if it's too tight or in the wrong spot. But definitely that would add complications to the procedure, it's a really great question though.
Okay, now we have team 23.4.
All right, hello, we are team ME 23.4 working with MODICA. Our topic is the utility bulkhead connector, and our team consists of Colleen Webb, Celeste Inoue, Matt Bisa, and Ethan Nelson Atkins. Our sponsor liaison is Will Gibbs, and our faculty advisors are Dr. Gilbertson and Dr. Hamel. Our sponsor, MODICA, is a startup company based here in Seattle that builds software-driven microfactory modules, which MODICA calls microfabs. Here on the image on the right is an example of one of MODICA's microfabs. Each microfab consists of an array of pods, each containing a 3D printer, CNC machine, or other small manufacturing device. The term pod, just think of a hollow cube that simply houses and powers whatever device is in it. And these pods each need to be connected to a power source, which MODICA refers to as their backplane. The backplane supplies electricity, data, fluids, and compressed air to each pod in the array. So essentially, we need to make a pod and a socket. We need to make a plug and a socket between the back of the pod and the backplane in order for these machines to run.
So kind of rehashing what Celeste was talking about, we have these microfabs, which consist of a backplane and pods. Inside each pod will be a small manufacturing device, such as a 3D printer or CNC machine. And we're recognizing that each machine might need a unique combination of electrical, data, compressed air, or liquid coolant in order to function. So our goal was to design a universal connector to simultaneously connect and disconnect different media connectors for simple installation and removal of pods via a pushing or pulling action. This will then interact with the mating face on the backplane, which will allow for a seamless connection of the pod and the backplane. So we'd love to introduce you to our friend Millie. Millie just recently bought a microfab and is really excited to experience all the different possibilities that can come with this type of manufacturing machine. She also bought a new machine that will really make her product more efficient and allow for her to make more of her products. So currently, this machine needs some kind of electrical input, some kind of data input, a compressed air input, as well as a liquid coolant input. But there's a problem with how she's connecting this to the backplanes at the moment. Currently, you have to connect each connector one by one until each one is all connected and ready for the machine to work. which is fine for one machine, but you have to remember that there's a lot of other machines that need to happen. So connecting it one by one is not very time efficient and is not very ergonomic either. The second problem is, what if there's a button that needs to be pressed to connect or disconnect the connectors? Such as this, where you have to depress a button in order to pull apart the connector. There's no way for Millie to reach around the pod or through the pod in order to actually interact with the connector. So what if there was a way that she could simply push the connectors together and have them all connect at the same time, and then pull them apart and have a seamless disconnection? This would make me really happy and be able to explore the possibilities of the microfab.
So going into some of the requirements for our connector, it will need to be able to disconnect and connect with 30 pounds, with less than or equal to 30 pounds of force. That is the average amount of force a woman can exert while standing. Next, it needs to be fit within an 11 by 2-inch frame, which is the size of MODICA's pods, as you can see on the right. And then it also needs to be able to handle 120 psi of pressure, no leakage, liquid temperatures between 50 to 212 degrees Fahrenheit, have 10 gigabytes per second data transfer, and handle 240 volts of alternating current. These are all industry standard measurements that we consult with MODICA for. And then finally, it needs to be able to handle about 2,000 cycles before failure. This is based off of the expected or hopeful lifetime of the pods, and then the envisioning that they will only need to be connected and disconnected semi-frequently, only if there's an issue with the machine inside. So then going into how we decided which connectors we were going to use. So we looked at a large variety of connectors, and as you can imagine, there was differences between all of them. For electricity, a lot of them are 2-prong or 3-prong. For data, we looked at USB, USB-C, or like an SD card sort of deal. And then finally, for fluid connectors, there's a lot of variation with those, specifically with like their body shape and then how they are connected. So what we looked at with all of those was how much they cost, how large they were, whether or not they fit our requirements, and then finally, how they physically connect and disconnected. Did you just have to put it in? Was there a button? Was there some sort of clamp, a twist, threading, all sorts of that. So then with our final decision, so for our electrical connector, we chose a wash down, a 3-blade, straight blade, plug in a socket. This can handle our voltage requirement. And this is just your standard, you just push it in and you pull it out for connection. For data, we chose a USB-C connector. This can handle our data transfer rate. And like the electrical, you just put it in and pull it out for disconnect. And then for fluid, we chose a non-valve quick disconnect with a button. So this could handle our pressure and temperature requirements, and there was very minimal leakage with it, but you do have to press a button for it to disconnect. So it goes right in, but you need to depress the button for it to be disconnected.
Once we had chosen all of our connectors, we needed a way to connect them all into a single connector, as our problem statement stated. So to do that, we made 4 separate boxes, one for the electrical, 2 for the fluids, and then another for the data, and combined those all into a cohesive unit. Here you can see is a CAD model of the 2 fluid connectors on the right, and then you have the electrical and the data connector housing. And here's our final design. Here's our final design where we have all those connectors that we had separated for prototyping, which made prototyping a lot easier. We didn't have to do all of them together when we were 3D printing them. But here's our final 3D print when we put them all together. So when we were putting them together, we had some problems with aligning all the connectors because there's 4 different kind of spaced out, and we have to get them all perfectly aligned to connect them. So we machined these locator pins, which you can see highlighted on the picture there, and that helps just connect them and align them when we're connecting them. And then here is the microfab face that we got, and you can see the connector in there. And here's the video of us connecting them. And next, we'll be talking about all the different designs when building the connector.
So yeah, going into more of the individual components, our electrical connector was just a push in and a pull out. So we needed to devise something that would just hold it in place and keep it steady as the overall frame was moving. So we came up with this holder that is held in place using a series of screws. And then we decided to do cycle testing on the individual components. So we 3D printed our all of our components, and this will not be the final material MODICA is using. So we did not do a full extensive cycle testing. We ended up doing about 200 cycles with the electricity connector, and we noticed no obvious issues or breakage. The only minor issue was that some of the screws came loose on the back after a little bit, but that's a simple fix with some Loctite or even a more powerful drill.
For our data connector, similar to our electrical connector, as you can see here in the video, it was easily able to push in and pull out. And so when we're prototyping our data connector, we really just had to focus on creating some sort of housing in order to constrain our connectors. And also, similar to our electrical connector testing, we hit 200 cycles. And as of now, we haven't noticed any signs of fatigue or any noticeable damage done to our prototype. But this is most likely due to the low sample size. We also anticipate that the set screws will most likely fail first after a long period of use, but we also realize that set screws are pretty secure for the most part, and so we recommend more testing to be done in order to see signs of failure.
So then our fluid connections, if you remember, we chose the same fluid connection for both compressed air and liquid coolant. So these ones push together simply enough, but then you need to depress a button in order to disconnect them, which kind of brought up a new challenge for us in how do we make sure that the user doesn't have to reach around a pod or through a pod to interact with the actual connector. So this made us develop a new button mechanism by which a horizontal movement would allow for a vertical pressing force, which is shown here in our final design. So the way we did this was we simplified it down into a 2D model. So you can see on the left here, the plug end of the connector is modeled with the 3D printed piece above. And then the socket connector is modeled by the 3D printed above that as well, with the addition of a button extension. So to design it, we took it into the 2D realm, which is shown here. And you can see as the red casing moves along, the blue button is depressed, which then opens the connector and allows for the two connectors to be separated. So taking that 2D model back into the 3D realm, involving our connector, we decided on a two casing system. So on the left here is the connector holding casing. So this is actually where the connector is being held, as well as the button extension that we talked about previously. The connector was held in with a locking screw on the back with pre-existing threads. On the right is the button depressing casing. You can see that it also uses the angled ramp system, which would then depress the button and would also allow for the horizontal movement to make the system work. So this is what they look like together. On the top right, you can see at the closed position, everything is sitting flush and the button is not depressed. And then on the bottom left, you can see it in the open position with that horizontal movement and button being depressed with that little bit of movement. So when we 3D printed it, this is what it looked like. We were able to prototype something that came out and worked. You can see on the left side again that the casing is able to hold the connector as well as the button extension. And then the button depressing casing on the right side is able to interact with that connector casing. So to bring it back into the 2D realm and relate these two, we match the colors. So as you can see, the red on both right and left pictures represent the button depressing casing. The gray is the connector casing, and then the blue is the button extension. Here it is again to show you how it works with in tandem with each other. This is the depressed position of the connector. And here it is working in our final design. As you can see, it is simply a push in and pull out without any type of interaction with the actual connector.
Revisiting our design constraints from previously, we met our first constraint of coupling decoupling force less than 30 pounds. We didn't explicitly measure this, however, when we tested it, it was easily able to push in and pull out. Next, we met our size constraint of less than 11 inches by 11 inches by 2 inches. As you can see here in the image on the right, it fits within the mock-up pod phase given to us by MODICA. And specifically, it has dimensions of 8 inches by 2.5 inches tall by 1.5 inches deep. And then for pressure, leakage, temperature, data transfer, and voltage, we assume that we met these constraints based off of the specifications of our chosen connectors, but again, we didn't explicitly test these. And then finally, cycles to failure. We are unsure if we will meet this constraint because we did not perform 2,000 cycles. We only performed 200 cycles. And so as a part of our future works, which we will talk about in just a second, we will recommend further tests.
So yes, for future work, we recommend once a final material selection has been made to undergo that more rigorous cycle testing. And then also further iteration should aim to try and integrate the connector more with the pod face and the backplane.
So we'd love to return back and check on our friend Millie. With our new development, Millie is now able to solve the two problems that were coming up. If you remember, the first issue was that you had to connect each connector one by one. With our new design, we've compiled them into a single connector that can simply push in to be connected. The second problem that came up was the button. If you remember, a button needed to be depressed before the connector could separate. We designed a novel button pressing mechanism by which a horizontal movement would create a vertical pressing motion as well, which allowed the connector to simply be pulled and separated. This makes Millie very happy and very excited to experience what the possibilities of microfabs can be.
First and foremost, we would like to thank our sponsor, MODICA, and Will Gibbs for providing us with an amazing opportunity to do a senior design project. We really enjoyed it and we really had a lot of fun. Secondly, we would like to thank Dr. Gilbertson and Dr. Hamill for providing us with guidance during this whole process. We really could not have done it without you. And then finally, we would like to thank Kenya for giving us advice during the past 9 months and helping us to succeed.
Thank you, and we'd love to field any questions you have.
This was not mentioned in your specs, but the thing that I immediately worried about when seeing this is just how tolerant you are of vibrations in the environment. Because some of those, the USB connection in particular, I think would be found with some of these. If, for instance, your pods were mechanically connected to a strong cooling fan or something, and there's persistent connections have been known to come to grief in high vibration.
Thank you. Yeah, that's a good point. I think our thought process was that the pod itself won't be being connected and disconnected very frequently, so it hopefully won't interact with the environment too much, but you bring a good point about vibrations, and I think that would be an excellent thing to explore in future work.
This was also very much more of a proof of concept because we weren't using the final material that MODICA will use, because we just 3D printed it, so it's just made out of filament. And yeah, it probably will break just based off of our model, but again, we're not too sure. We only performed 200 cycles, so.
Do those fluid connectors seal on the backplane side when they're disconnected, or do they need a some kind of would they need some kind of blanking plug if there's not if all the pods aren't installed?
So we were working under the assumption that the backplane would be a smart backplane, if you will. So flow would be stopped using some type of electromechanical system. So we were not worried about flow continuing when disconnection was made.
Just a quick question. I don't remember from your diagram, but do you have all the male ends and the female ends on the same side? Or are they on different sides of your connector?
Yeah, they're all on the same side
Okay,
for each side, yeah.
okay, gotcha. Which side is on the pod side and which side is on the backplane side? Is there a reason you chose that?
So we have, I guess the side with the female side is gonna be on the backplane side just because it takes up a lot more room, which isn't available in the pod.
Gotcha, makes sense.
Came up with that little pull mechanism for the liquid and air.
That would be neat.
Do that. That's genius, but I like that. Very simple, straightforward, got to the point. My question is not necessarily on your guys' end of it, but you're still basically putting a machine into this pod and you're gonna have to connect stuff up to your connector into that. How does MODICA work on kind of on that level? Like they just have cores, they plug it all in and then shove it in like you do a toaster or
So the idea of MODICA's pods are for it to slide on rails. And so like you just simply use a horizontal force and then you'll hear a click. And then that's how you know that the pod end is connected to the backplane end.
No, I'm talking about connecting whatever 3D printer you've got to your interaction plate on the back. Like when you take your 3D printer or your CNC machine, you put it inside the pod, you're still having to reach around and plug it into the box, right?
Yeah, so within the inside of each pod, there will be mating surfaces, plugs and whatever, in which the built-in connectors of the machines can interface with, and that will be very user-centric. Our goal was to universalize the pods themselves. Right. And so future work was also discussed that the machine itself, when plugged in to the backplane via the pod, could talk to the backplane and say, I need X, Y, or Z inputs, and then supply those and not others.
All right, welcome everyone to the last session for today. In this session, we'll have two teams from the same company, SDI. For those of you who are here for mechanical engineering students, we're actually going to move for the third session over to room C6. But that's after the two presentations. For now, we're going to have ME 23.6 SDI present.
Welcome, everybody. We are Team ME 23.6, working with our sponsor company, SDI Engineering, on the extended cycling. Before we begin, I'd like to introduce the team as well as our sponsors and our faculty advisor. We have Dylan here, Matthew, myself, Tyler, Matt, and Jaden. Our industry sponsors include Dr. Bob Sterling, Dr. Steve Tomlinson, Dennis Riddell, and Boone Tate, and our faculty advisor, Dr. Frank Shee. And now we'll give a brief overview of what we'll be going through during this presentation. We'll introduce SDI Engineering. After that, we'll define some terms so no one gets lost, and we'll go through our problem motivation and statement. After that, we'll introduce the core principle to our project, Mechanical Advantage. And then hopefully we won't confuse everybody with the mathematical model and go through the physical prototype, and then we'll end our presentation off with the future recommendations and a Q&A. So what is SDI Engineering? Well, they're a full cycle engineering firm that deals mostly in mathematical models and development of simulation.
They also touch on R&D as well as design and analysis. Some of their most notable projects include ARES, which is an aerial refueling simulation, as well as Gearsim, which is a landing gear simulation.
If you don't know by now, we're working with bikes, more specifically the part where you pedal. So before we dig into our project, we'll give you a few terms that we will reference throughout this project and hope you don't get lost. So on the left side, we have the bottom bracket highlighted in red. This is on the bottom of the bike frame that spins freely, and this is where the crank arms attach. On the right side is where our crank arms highlighted in yellow. So there's a non-gear side, which is on the left, that goes on the left side of the bike, and then the gear side, which is on the right side of the bike. We use clock notation to give the position of each crank arm, and this is 12 o'clock being up, 6 o'clock being down, and 3 o'clock being forward relative to the bike.
And so now that we've gone over a few key terms that we'll use throughout this presentation, we're going to introduce the problem motivation. Originally, our project began as a passion project by the co-founder of SDI Engineering, which he then handed down to us to continue. The idea behind it is simple. By increasing the length of the crank arm, you can get more torque and more power out of your biking. What does more power mean? Well, when biking against the headwind, it becomes easier. When climbing up hills, it becomes more manageable. And as a product that will be added onto existing bikes, it can be marketed as something to make riders bike easier. So that brings us to our problem statement. Our problem is to examine the patent of an existing patent of SDI Engineering called the Extenda. After talking to our sponsors and giving helpful aids like the video on the right, we came up with 3 criteria to meet in our project. The first being designing an extension and retraction mechanism that increases mechanical advantage. The second is making sure that the system is purely mechanical. That means no actuators or electronics. And then third, making sure that the system fully retracts at the 12 and 6 o'clock position.
Now we'll go ahead and introduce the core principle to our project, mechanical advantage. What is mechanical advantage, you might ask yourself? Well, simply put, it is a method by which we can amplify force. Take this simple lever arm here. We'll say on the right hand side, the input force is FA. We have our 2 lengths A and B, which will be measured from the pivot point, and our resultant force FB. So how can we amplify the force of this system? Well, why don't we give some values to these? We'll say our input force is 14 pounds. The 2 lengths A and B are now 4 feet and 2 feet respectively. And given by the equation here, if you divide the 4 feet by the 2 feet, you get 2. Multiply that by our input force, 14 pounds, and we get 28. Here, in this system, we have successfully amplified the force by a factor of 2. So what does this look like on a bike? As seen before, we have a crank arm, chainring and chain, our input force of FA, resulting force FB, and the 2 lengths A and B. So traditionally, how would we increase the mechanical advantage of this system? Well, traditionally, you would usually shift to a smaller chainring, thereby increasing the length B, like so. And with this case, we can increase the mechanical advantage. But our design differs from this. Instead of varying the chainring by decreasing B, we instead keep that constant and vary the total crank arm length in cycle. This can be noted by X, which is the additional length that we're adding to the total crank arm. And with this design, we can increase the mechanical advantage of the system. We'll go on later to explain why this design differs from that of the traditional.
In this next section, we'll be covering results from our mathematical model, our physical prototype, and our magnetic locking mechanism.
And now for our mathematical model, we modeled this in both MATLAB and Simulink. And one of our main goals for this model was to show the performance increase in our bike using the extended crank arm. And we were specifically looking at the torque versus the revolutions of the wheel. And this means for the team that we will be able to validate our design concepts to meet the goals we set out, as well as being necessary to see the performance increase for our decision-making process. So there are 3 things that we have for the scope of the model. One was to ensure that the design concept was mathematically sound. The other one was to create a testing platform to be able to test multiple different variables. This may include the hill gradient or also the road conditions. And finally, the third one was to compare the stock bike with the extended bike and looking specifically at the mechanical advantage they provided. Over here, we have a graph of torque versus revolutions. And it's with the extended bicycle in blue and the stock bicycle in red. And as you can see here, the stock bike is a constant line with no deviations. Where the extended bike is not a constant line, it has oscillations as observed. And from this, you can actually see that the extended bike does increase the torque, observed through the cycling. Looking over here, we now have a speed analysis of our bike, and the extended is still highlighted in blue, where the stock bike is in red. And the extended here has higher speeds compared to the stock bike, as you can observe. And the oscillation you see there is also in line with the pedaling of the extended.
Yeah, in this next section, we'll be covering the prototype. We prototype the extending and retracting system and also the locking mechanism. So this image here is our non-gear side crank arm, with the image below being a fully assembled and retracted system, and the image above is a fully extended and assembled non-gear side crank arm. This image here is our gear side crank arm. Starting with the largest part, we have the gear side receiver. The gear side receiver is what connects to the bottom bracket on the bicycle and has a slot that the pedal side piece would fit into. The pedal side piece is what connects to the pedals on the bicycle and is what causes the extension in the system. There are screws and springs, with the springs hooking onto the screws, which cause the retraction in the system. Additionally, there's a plate that allows us to access the springs and screws internal to the crank arm, and fasteners to secure the plate in place. And finally, if you have noticed, there's a slot here in the pedal side piece that the bolt would fit into so that the pedal side piece does not slide out of the crank arm. And to the right, we have a section view of our machined CNC prototype.
So here we have our fully manufactured non-gear side piece with the hair screws in place in the slot. Similarly, we have the gear side crank arm with the hangers and the slot as well. Here's the pedal side piece, again with the hanger screws, and this is the piece that actually does the extending. So here's it all assembled together with the gear side having the gear mounted on it and each crank arm having the pedals in place. So let's see it in action. So here our rider is using our extended crank arm, using a normal cycling motion. It may be kind of hard to see, but you don't really see much extending going on. But in this next video, with a different technique that we use, with a more of a pull up and push out with the foot, that's where you get the extending and the needed mechanical advantage. So how does this feel to the rider? The 2-centimeter extension doesn't really have an effect on the comfortability of the rider. And as you see on the right side of the screen, the different types of springs that we tested and used. Unfortunately, all the springs that we used were too weak to be able to retract at the 6 o'clock position. That being said, if we use a stronger spring, the rider wouldn't be able to use their foot to extend the crank arm. And like in the previous slide, we saw that there's a new technique. This may be kind of weird and difficult to learn at first, but it's just like riding a bike. There's definitely going to be stress on your quads and your core. And since this is just a first prototype, there's definitely a lot to learn.
So in tandem with our extension and retraction mechanism, we also developed a locking mechanism. This locking mechanism satisfies the third point we went over earlier, where the system is supposed to retract and stay retracted at the 12 and 6 o'clock positions. We have also made the system inspired by magnetic cabinet locks, those things that keep kids out of the drawers late at night. And it's unlocked by a magnet, as you'll see in the next slide. So we have the magnetic cabinet lock, in 2 states. On the left, we have it without a magnet, where the hook kind of extends out and locks the system. And then on the right, we have it with the magnet, unlocking the system. And if we go to the next slide, we'll see an overview of our design. Essentially, the bike frame in pink is connected at the base to the crank arm in yellow. And then there's 2 magnets we want you to pay attention to. There's a blue magnet, which is on the crank arm and rotates with it, and a bar magnet, which is connected to the bike frame. When the crank arm rotates and the 2 magnets overlap, then the system unlocks, allowing for extension. In the next slide, we have a visual of we have a prototype showing the mechanism where the system, as it approaches the table, unlocks, being allowed to extend. And then once it's outside of the range of that magnet, and it's still extended, once it retracts, it is no longer able to extend.
In the future, we recommend creating a more rigid locking mechanism and incorporating it into our prototype. We also recommend incorporating sensors such as a strain gauge and an RPM sensor so that our prototype and mathematical model can work together. We also recommend running tests with these sensors to validate any assumptions we made in our mathematical model. We recommend doing a fatigue test with our crank arms to find the life cycle of our device. And finally, after incorporating the sensors and putting our device through rigorous testing, we recommend creating another prototype that addresses all of the issues in our current prototype. And before we conclude, we'd like to make a few acknowledgements. We'd like to give a special thanks to SDI Engineering for giving us this hands-on opportunity with this project. We'd like to also thank our faculty advisor, Dr. Frank Shi, the Mechanical Engineering Department, and also the Project Center for all the guidance and feedback throughout this project. Additionally, we'd like to give a special thanks to our lab manager, Mauricio Gutierrez, for all of the help throughout the fabrication process of our project. And finally, we'd like to thank our friends and family in the audience today for all of the support throughout our academic endeavors. With this said, thank you for listening, and we'll now be taking any questions you all have at this time.
How did you guys determine how much extension to design for? I think you said it extends up to 2 centimeters. How did you come up with that number?
Originally, in the beginning of the process, we were talking with our sponsor advisors about kind of what they thought about this project. And originally, they gave us this figure of how much mechanical advantage we would get based off of how far it would extend. Originally, we were given a figure from like 1 to 4 centimeters extension, and we decided to choose a happy medium in 2 centimeters, just to make sure that when we extended it, we didn't make a prototype that would just break off the bat. And we figured 2 centimeters would be just enough so that it had enough structural stability that when we built it, it wasn't just gonna lop off and break. Good question, thank you.
So since it's just a prototype, do you guys think in the future there would be like some sort of like special shoe to work with this, or just keep it as any type of shoe for your product?
So at the moment, we have foot cages that your foot could attach to, and most shoes would be able to fit into this device.
Yeah, I'm back.
So with a product like this, could you guys talk a little bit about how it would be used for like when someone gets the product, like how they would install it, like how long it would last, that sort of thing?
So the product that we made is designed to be added on to like the majority of, a lot of bikes are made with this bottom bracket attachment called a square taper bottom bracket. And so the attachment is pretty similar. It's like standardized out there. So we looked into these standards. And if we wanted to design it in a way where we could add it on to existing bikes, we just need to make sure that when it like went on to the bottom bracket, it'd be the same. In terms of cycling, that's for future testing. The current product we have is not made for cycling. It's made more as a proof of concept to show that like the mechanism would work. But in future iterations, we would definitely look at ways to optimize the weight and improve cycling to more of what is seen out in the world right now.
So the 2 centimeter thing, it seems like that's less than half of the length of that crank. So how did you get such a huge oscillation?
Could you repeat that question again?
So I remember when you said the A over B and the distance, the force, could be, it looked like you had quite a big force difference, and the oscillation that you showed in the graph of the square oscillation, then afterwards the other one. From 0.4 to 0.6.
So for that part of the simulation, when we were inputting the forces, the simulation that we had acquired and modified, I exaggerated it by about a factor of 10. And in order to be able to see the main differences here. The main differences here, you can actually see that the torque is not as high as you'd expect it to be. Mainly because of the 2 centimeter extension. Obviously, with a much larger extension, you'd see a much higher number. But with only 2 centimeters and very little room to work with for our crank arm, we were satisfied with what we were seeing, and it still proves the point of the torque does increase.
All right, now we have CS 23.15. Yeah.
Hi, everyone. Welcome. We're group CS 2315, Project Gearsim. My name is Eugene Keehan. And our advisor is Dr. Yingwu Zhu. And our sponsor team at SDI Engineering consists of Dennis Verdell, Dr. Philip Richards, and Boone Tate. So first, I'd like to give a little background on who SDI Engineering is. SDI Engineering was founded in 1994 by Dr. Bob Sterling. They focus in research and development and are a specialist provider in engineering services for providing applications for mechanical systems and structure applications. And they also focus on providing software tools for a variety of analytical uses, such as analyzing a landing gear, and the name of that application is Gearsim, and is actually the project that we've focused on. So what is Gearsim? Gearsim is a landing gear and subsystem analysis tool for aircraft landing gear. It aims to reduce the amount of resources and effort required during the product development lifecycle, and it does this because it allows the user to perform countless tests on
a landing gear virtually, and so it saves the amount of time that would be required for an actual test. It also provides a high level of modeling detail for someone who doesn't necessarily have the high expertise in modeling, but still wants to be able to perform the tests and analysis efficiently. So now for some challenges and opportunities regarding Gearsim. So Gearsim was originally developed in MATLAB, but SDI Engineering wants to focus on converting the original MATLAB version into a more modern version using C++ and the Qt framework. And so the current version of Gearsim has actually been developed into a prototype for this Qt version, but it only exists right now as a user interface. And so our main task has been to extend upon the previous, the original prototype for it and actually implement the core functionality. And one of the features that's missing right now is the ability to load numerical data in, which is required to actually run the analysis. And so the data is actually designed for MATLAB, but we need to figure out a way to read the data so that it is supported by the C++ application. And another feature that is missing is just the basic functionality of being able to create open and save projects.
So our goal for our project was to build up a Gearsim prototype. So to do this, we had to improve the front end and back end components. To ensure that to ensure our work is easily understood and extended by Greek developers, we wanted to make a robust storage architecture for model data and provide an API that connects the front end inputs to back end processes.
Now, in this part of the presentation, we will go over the architecture of Gearsim. In the first figure, we have the use case that demonstrates how Gearsim is used by engineers to test and improve on landing gear models. So let's say that there is an SDI engineer named Jim that wants to test and improve let's say that there's an SDI engineer named Jim that wants to test the landing gear model, and he first at the start of the process he will log into Gearsim, and he will face with two major decisions. Either he wants to load a model or create a new one. So for the sake of this example, let's say that he wants to load a model. Next, in the dynamic menu, he will be able to view all the parameters of the model, and he could go through a loop of populating the parameters and resimulating the model. After going through a variety of combinations of the parameters, he finally finds a set of parameters that works really well for his model, so he chooses to save that model. Next, we will dive into the system view, where we will explore all the low-level components and its interaction with the operating system. To begin, the authentication is handled by Microsoft Azure that deals with the login credentials of the customers. Next, we have in Gearsim, there are the components and pages that are written in QML. And in order to render these properly, the Qt resource system finds the necessary assets to ensure that the visual components of Gearsim are rendered properly. So while Qt handles the GUI rendering, C++ manages the communication and interaction with the operating system, file system. So at the start of initializing the rendering, C++ goes and finds the configuration files in order to initialize the global state of the system. And while Gearsim is running, C++ will So while Gearsim is running, customers may want to interact with files, And so, Gearsim uses the file IO to allow customers to read, write, and load the content into the file system. So next, I'd like to share with you the tools and technologies that we use in the development of Gearsim. First, we have C++, our core programming language that allowed us to build the backend component of Gearsim. And next, we have the Qt framework, more specifically, the QML language that allowed us to define the user interface as well as the behaviors of the front-end component. So in addition to the technology stack, we also use a variety of tools such as GitHub to manage our code base, and we use Microsoft Teams to communicate and collaborate with our team. And while Visual Studio Code allowed us to write and edit our code, Qt Creator, the IDE of Qt, was the main tool that we used to develop Gearsim.
So next we have our milestones that we have. We have 4 milestones. Our first one is the imitated documents. So the imitated documents go through both the design and also the scope of our project and also our project plan as well. And this helps us get familiar with our project in general at the beginning. Next would be the Gearsim API. And the Gearsim API took a lot of the backend components to help it work with the front-end components. And this includes such as opening and creating a new project, accepting user data, and also logging the log data as well. Next, we have data storage, and data storage deals with data architecture, user inputs, as well as the dynamic content that we have in Gearsim. Then we have shipping, and shipping includes creating a deployable folder, having an installer, and being able to send that to our computers. Also testing and documentation as well for our program. So our MVP, or our minimum viable product, includes 4 main features. The first feature I'll be going over is the history log. Now, the history log will keep track and record all of the changes the user made on the user input. And these changes will be stored each time the user saves the project. And the user will be able to revert the changes to any time and save in the history log. Then next would be deployment, and deployment includes the installer. And the installer, we create the installer by first using applications by Qt to create the deployable folder. And then you would next use something called the maintenance tool to be able to create the installer.
So another major part of our MVP was the dynamic content. So the interface has to reflect the user's needs. So depending on the user's current model, the interface needs to dynamically update with relevant information. Another important aspect of the MVP was the data file API. So the API connects the user inputs to the backend where it can be saved into a file. It also serves to retrieve these data files and unpack the contents for display or editing. As for our status, we have created a robust and extensible API that can handle creating and loading files and save files. The API features allow us to take a snapshot of the current in-progress model and roll back fields based on the timestamp. Our UI has also been structured in a way to make it easy to maintain and extend later on. Each component has a clear purpose, but it's also made abstract so that it can be used in other contexts. By using our API and event-driven callbacks in our components, the new Gearsim is much more powerful than before. For our final status point, we have deployed our application. Gearsim has an installer and can be used on any Windows machine. And now I'll hand it over to Richard for the demonstration.
So my partner gonna do the demonstration of the Gearsim, the entire prototype that we have done for the entire academic year. Sorry about that. We have technical issue about the slides, so we will prepare for you an installer so that you can click on and then install on any machine. So right now we have the installer for you. If you click on it, it will open the installation. And it will be like a very small installation for you to select, and then it will go through the whole installation process. You can just like click on next. There will be like a folder. It will be the installation folder for you to select the destination. Right now we can just name it like demo 1 or 2. Let's call it demo 2. And then we can just continue to click on to do the installation. Give it some time and then we can start it. So right now, after install on Gearsim, we can just like open the Gearsim from the start menu. First of all, like this one is on your machine. You don't need to you don't need to know your location. Well, you do need to know your location, but this is on the start Windows menu. So now you can click on the open. And there will be the Gearsim, there will be a Gearsim application running. There's a lot of things going on. The first thing is the top menu bar. You can see on the screen, there will be like a green component on the top menu. The second one is the create project. The create project, just like we create a new project. And the last one is the recent file. The recent file is like when we open or modify something, it will be displayed on this component. So we want to. So right now we can just go through with the create a new project. We go with the narrow body commercial aircraft. And then then we jump into the second page called configuration page. In this configuration page, there will be a bunch of options that we need you to choose. For example, we have to choose test type. We can from now on everything kind of branched out. So for example, you have the emoji. When you click on the emoji, you going to select analysis. It will change content of the select analysis page. If you go back and then you select energy, it will have different configuration for you. For now, we're gonna do with the whole aircraft. So in the whole aircraft, you see that we have different select analysis, like different type of maneuver, like braking maneuver, ground maneuver, anything like that. So this is one of the first step of the dynamic content that we implemented during the presentation, during the departure. So now we can go to the landing maneuver. Okay, just give it a name. So yeah, we also implement some very nice feature in back. So it will check for you. For example, you install something. If you create something, you already have a folder with the exact same name. It will give you a warning or something like that. Okay, so we will talk about the dynamic content that we mentioned about. This is the general main page. The general main page will load on the configuration page and use those options to render this dynamic view. For example, you can check on, there will be a night tab on the right side that will give you all the metadata that we selected for this project. We have the model, the narrow body commercial aircraft. We have the test type. We have the analysis that we selected. So Gearsim will use the information and then render the content. The first one is the leftmost. The leftmost menu. That is what we call the model browser menu. The model browser menu will basically like select like scenario asymmetric aircraft like on the top level. And then based on the model browser menu, we can select. So basically, you guys. You want somebody else to come back? Sure. Okay. Okay, so we can get started from here. So we have the application. So let me go back. So let's talk about the first on the leftmost. We start from the left to the right. So on the left, we can see that there will be that's what we call the model browser menu. You can set the model that you want to do the operation, or you want to select files, something like that. So from the levels menu, from the model browser menu, you can select the what we call the subsystem menu. The subsystem menu will contain all the components that are required to render the data field. For that, for example, the general scenario parameters will contain the simulation time step, and the interval. So when you click on different subsystem menu option, for example, if you click on the aircraft initial condition, it will generate a list. We have internal data file for all the configuration for all the configuration. So it will generate a list so that the subsystem on the middle component will render everything for you. So it will generate, for example, if you go back to the general scenario parameters, if we click on this one, it will give you a list of simulation time step, and info. The middle component, the subsystem class will take that list and render all the input field. Inside with input field, we will create another input component. We will fetch that component items into that input field. We have the simulation time, and then we have the variable name, we have the input field, and we have the question mark to indicate the long description for this variable. For example, like the time step, we can have like the simulation time step. For the interval, we have interval to set the data, so that's kind of for. Another thing that from the input is that if you don't know what type of unit that input is, you can just like delete all the data, and then it will show you the placeholder to indicate the unit of that input. So that is just like the dynamic content that we mentioned about. This on the right side is the log. The log is about like how you want to change. This is the log. So the log is like when you, so right now when you modify something on the data field, it will update on the log for you so that you can know what data, what time, and what data field you have just updated. Let's go with the complicated one. For example, like this one. This one is initial aircraft downward velocity. We want to change it to let's say 35, and then we hit save. It will save to local. It will save to the file system for you, and at the same time, it will append a new log onto the right component. So with this log item, you can just click on it. It will give you a warning. Do you want to revert back to the change? It will give you like the old value, for example, like 3 at this data field, and you hit yes. You will see that it will go back for you at this label, at this data field. Okay. So yeah, that is the dynamic content, and also the the log data file. So we also have, the team also have some extension to the application for simple like shortcut or key binding. If you see on the top menu right now, you can see that there will be like a bunch of options that you can select for example, a new file, open file, save as, or exit. Right now we can just like click on it, it will go back to the first page, or you can hit Control N. Let me hide that. If you can hit Control N, it will go to the first page for you, and it will destroy everything for you, and then you can start from a new one. Right now, you see on the recent project, when we created the demo 7, it will update the recent file and then put it there for you. Everything will happen behind the scene. There will be a file service. There will be like a file service. We wrote that file service in C++ that handle all the loading data, reading data, and display on the application. The QML will basically fetch that data and display on the application. And another feature we want. Okay. Yeah. So another thing is the open file. So one last feature is the open file where you can, for example, if we have someone send me a different project and want me to continue to work on that, we can choose that. For example, I can go to with the demo. Right now I just create open demo 7. Let's do like some demo 4. And then it will still open everything with the different title name and everything like that. So that is the our demonstration for the application. Thank you, Jim. So yeah, there always one slide at the presentation. What we learned during this project is that communication is key. We agree that we need to spend more time communicating. I think communication is the key to success in this project. The second thing is the high-level design document. When we for two project, we kind of lost we need some documentation, and that is something that we plan to do for the next team if they want to continue this project. They have some documentation to refer to. That would be nice. Yeah, I don't think I have time for more content, so we can just go to the Q&A section.
How easy was it for you to pick up the project from the previous team?
I can answer that question. So I actually do what I learned for this project is that I'm gonna install for example, we're using Qt and C++, right? So I'm gonna install that in my local machine. I start to download the build from the sponsor. I'm gonna mess up a little bit, try to change a couple things, see how it goes. And then maybe like try to read up some documentation with the Qt framework, and then apply that Qt framework to create some, for example, like I want to change the color of the top menu bar. I want to change it to green. How can I do that? And just like Google, and with the help with some extra tool. That's that. Yeah, that's my answer. That's how I learned. I'm not sure about the rest of the team. So any question?
So what does the output of the tool look like? So for example, if your simulation shows that the landing gear can't handle the stress or something like that, does it just have a text output or?
So there isn't actually, we haven't gotten to the actual portion of the simulation, so that hasn't been implemented yet, but our main focus was actually getting the numerical data loaded into the application. And so for next year's team, maybe they would focus on using that numerical data and inputting that into the software that's used for the running simulation.
There's probably, there's one more presentation left in some of the other rooms, so C5 and C6, if you want to go check out the last presentation. After that, we have the, you can go check out the projects. They're all out here in this level and the first level. So thank you all for coming.